velocity less than the upward movement of air can reach the filter. Thus, as can be seen in the plot, particles smaller than 15 micrometers collect on the filter with high efficiency, whereas larger particles fall out of the device and have low collection efficiency. Let's consider inertial forces now that act on a particle, which leads to impaction, like a bug hitting the windshield of a car. The windshield causes air to move up and over the car. The force of drag will cause a small bug to follow the airflow over the car, avoiding the windshield. In contrast, a big bug, like a grasshopper, resists drag because of its inertia. If the inertia of the big bug is sufficient, it deviates away from the airflow to hit the windshield and make a big mess. This process is called inertial impaction. The concepts of particle relaxation time and stopping distance are used to describe inertial forces. The particle relaxation time is how long it takes a particle to relax to its new conditions. It is proportional to particle density and diameter squared, which is exactly the same as we saw before with terminal settling velocity. The stopping distance is the distance that the particle will move along its original direction until it relaxes to the new conditions. It is calculated as the initial velocity times the particle relaxation time. In the figure from the video, the small bug has little inertia. It relaxes fast to new conditions, having a short relaxation time, or tau, and thus moves only a short distance toward the windshield, having a short stopping distance, and it passes over the car without hitting the windshield. In contrast, the big bug has lots of inertia. It is slow to relax, has a long relaxation time, has a large stopping distance, so it moves away from the airflow streamlines and hits the windshield. So now we can use these relationships to compute something a bit more related to occupational health, such as how far will a silica particle be thrown from a grinder. Going back to the same table that we used previously with particle diameter in micrometers and nanometers in the first two columns, the middle column shows particle relaxation time, tau, in seconds. The last two columns show the distance thrown, or stopping distance, in both meters and feet. Small particles relax very fast. It's only until we get to the largest particles where we get appreciable movement. A 10 micrometer particle is thrown only 0.02 feet, which is about a quarter of an inch. In contrast, a 100 micrometer particle would be thrown much farther, about 2 feet. So the eye protection required for the worker shown in the picture is to prevent ocular damage from impact of very large particles. Inertial impactors use this inertial property of aerosols to remove large particles from an airflow. Air is forced through a nozzle, which accelerates the air into an air jet. The air jet impinges on an impactor plate, causing the jet to abruptly turn 90 degrees. Small particles with little inertia relax to the change in direction and pass around the plate, often to be collected on a filter. Large particles, in contrast, have enough inertia to hit the plate and be removed from the air. In this way, small particles can be analyzed separately from larger particles. Impactors are usually characterized by collection efficiency by particle size, such as shown in the upper right. Large particles hit the plate almost every time, having a plate collection efficiency of near 100%. Small particles, in contrast, almost never hit the plate as they flow with the airflow, having a low particle collection efficiency. The particle diameter for which 50% of the particles collect is often referred to as the particle cutoff diameter and used to describe impactor performance. The light blue personal environmental monitor shown in the lower right is designed to collect particles smaller than 2.5 microns onto a filter after an impactor section that removes particles larger than 2.5 microns. Cyclones are another type of important device that use inertial impaction to separate large particles from an airstream. The airflow enters a cyclone and spins several complete turns before exiting. Large particles hit the walls of the cyclone and move to a chamber at the bottom of the device called a grit pot. Small particles remain airborne and pass out of the cyclone. Respirable cyclones are commonly used as lapel-type samplers to measure particle exposures, with the smaller particles that can enter the deep lung exiting the cyclone and collected onto a filter for subsequent analysis. Air is pulled through the cyclone using a belt-mounted air sampling pump. Industrial cyclones for air cleaning can be very large and serve to remove large particles nominally larger than 10 micrometers or so before being exhausted in dusty industries such as woodworking. Now we will consider Brownian motion, which leads to diffusion. So far we've been discussing large particles like the green 10 micrometer particle shown on the right-hand side of the slide. Very different forces are important for small particles that approach the size of gas molecules, like the red 5 nanometer particle shown in the slide. These particles randomly jitter because of the bombardment of gas molecules. This movement is called Brownian motion and is important for particles smaller than about 100 nanometers. Brownian motion leads to diffusion, which is the net movement of particles away from where they started. Brownian motion is characterized by the diffusion coefficient, capital D. Shown in the equation in the yellow box, the diffusion coefficient is directly proportional to the fluid temperature and inversely proportional to particle diameter. So if the particle temperature increases, gas molecules move faster and the diffusion coefficient becomes larger and the particle will jitter more. Unlike other forces that we have seen so far, Brownian motion is inversely proportional to particle diameter. Thus, this equation tells us that smaller particles will jitter more due to Brownian motion than larger ones. Brownian motion causes particles to be displaced. Consider, for example, if we line up a bunch of particles at time 0 and then allow them to randomly jitter. After some time, these particles become displaced away from the center, randomly moving in any direction. The net displacement can be expressed as the root mean square displacement, which is simply the square root of 2 times the diffusion coefficient times time. Shown in the table at the lower right, a small particle, like a 5 nanometer particle, will have a large diffusion coefficient and therefore a large displacement due to diffusion, whereas a larger particle, say 300 nanometers, will have negligible displacement. If we look at this equation, the more time we give diffusion, the more displacement we'll have. To get a better feeling for how particle size dictates what forces are important, let's compare how far a silica particle moves in 1 minute due to Brownian motion and gravity settling. Again, I show particle diameter in micrometers and in nanometers in the first 2 columns. Then I provide displacement in 1 minute due to Brownian motion in column 3, and that due to gravity settling in column 4. Finally, in the rightmost column, I show the ratio of these displacements, that due to Brownian motion divided by that due to gravity settling. The force of gravity dominates for particles larger than 1 micrometer, whereas the force of Brownian motion dominates for particles smaller than 100 nanometers. For a 10 nanometer sized particle, Brownian motion causes 424 times more displacement than gravity. However, the distance moved in 1 minute is still very small, 0.002 meters, or 2 millimeters. To put things in further perspective, we need to change the scale of things that we are considering. So here, for this plot, on the y-axis, I show the distance the particle is displaced in 1 minute, but instead of showing this data in meters, I show it in micrometers. The x-axis is particle diameter that we are familiar with. For perspective, I add that the mean diameter of a human alveolus is 200 micrometers. Again, we can see that for particles smaller than 100 nanometers, diffusion dominates over gravity settling. These particles, if allowed to stay in the alveolar region for 1 minute, will likely be displaced a sufficient distance to hit the wall of the human alveolus. Diffusion can be used to remove small particles by passing a particle-laden airstream through a screen. Brownian motion causes the smallest particles, say with a diameter of 10 nanometers, to jitter more than medium-sized particles, say a 100 nanometer sized particle. The smallest particles, therefore, have a high probability of hitting and collecting on the screen, having a high collection efficiency. In contrast, the medium-sized particles tend to follow the airflow, pass through the screen with low collection efficiency. In my laboratory, we have used a combination of inertial devices and diffusion screens to develop what we call the Personal Nanoparticle Respiratory Deposition Sampler, or NRD sampler. The motivation for this work was to measure nanoparticle exposures separately from larger particles in a workplace, because sometimes nanoparticles have more biological activity than other airborne particles, even if they're made from the same material. In this device, particles enter a respirable cyclone, which removes the largest dust, nominally that larger than 4 micrometers, and may cause downstream components to fail. An impactor then removes particles larger than 300 nanometers, leaving only the smallest particles airborne. Then a series of diffusion screens collect nanoparticles with an efficiency that mimics deposition in the human respiratory system. These nanoparticles can then be analyzed separately from other airborne particles. The entire sampler can be worn on the lapel and works with traditional belt-mounted air sampling pumps, and analysis can be done by traditional analytical chemistry methods. Electrostatic forces cause the particle to be attracted or repelled to other objects, such as a fiber used in a respirator. These forces can affect any size particle, and just like magnets, like charges repel and opposite charges attract. These forces can be very important, but a detailed description is beyond the scope of this course. However, I will give some examples later of how electrostatic forces can be used to improve the efficiency of filters. The forces that cause particles to adhere or detach from a surface are important in determining the stickiness of a particle. Adhesion, primarily due to van der Waals force, is an important force that is proportional to particle diameter. This force also goes up with relative humidity. You can understand that as things get stickier when they're wet. Detachment is proportional to particle diameter squared, or particle diameter cubed. If we consider a particle on a filter being shipped by FedEx, larger particles will have much greater likelihood of falling off the filter because they have more weight and want to keep moving when a shipping box comes to an abrupt stop as the package hits the ground. Air currents also can pick up particles such as wind-blown dust from a standpile. The net result is this. The force of adhesion is fairly moderate with all size particles. However, detachment forces are much stronger for large particles. Consequently, nanoparticles stick really well, and particles larger than 10 micrometers detach from things really easily. Now we're going to consider coagulation, another important phenomenon for nanoparticles when particle concentrations are very high. In this plot, I show the evolution of particle number concentration in number of particles per centimeter cubed by particle size. 1 centimeter cubed is about the size of the tip of your